GPU programming. It's that strange cousin to the more familiar CPU. It can't quite do as much, it doesn't feel quite as general, but what a GPU does, it does with massive parallelism and tremendous speed. And if you're good at programming it, if you know the constraints and the tricks, if you're not afraid to think about things like optimizing register allocations, it's a world full of possibility. And it's a world I've not given enough credit to in the past. I have mostly associated GPU programming with graphics programming, for obvious reasons. But that's selling it short. The GPU is just a playground for all kinds of parallel programming. And my guest this week is here to show us quite how varied and novel a career close to the GPU can be. I'm joined this week by Agnès Leroy, and she spent most of her career programming physical simulations for everything from dentist drill bits spinning in your mouth to hydroelectric power stations. And there are plenty of juicy details we get into just going through all that as we work our way towards her current GPU job, which is optimizing encryption algorithms. And if you think you already know plenty about encryption, here's a question for you. Is it possible for me to give you an encrypted file and have you process the contents without decrypting it? Processing without seeing inside, that shouldn't be possible, should it? But it is. It actually is. Secure processing of encrypted data. And about 30 minutes into this podcast, you're going to hear me trying to wrap my head around that idea in real time. It is a mind-bending idea. But once it sinks in, it speaks to some terrific possibilities for things like keeping control of your privacy in a cloud-based world. To get there, it's all going to depend on someone making that processing fast enough. So, we've got a lot to get through. We've got Agnès' entire career to get through, so we best get started. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Agnès Leroy. Joining me today is Agnès Leroy. Agnès, how are you?
Very good. Thank you very much for having me today.
Oh, pleasure. We've both just got back from a holiday vacation, so we should be very relaxed and hopefully still technically sharp.
Yes, definitely. I hope.
I've got to admit, I'm going to do this on hard mode because not only am I asking you to talk tech when you're freshly back from holiday, I want to start right back at the start of your career. So you're going to have to go into the mental archives.
Yeah, because I think when we talked about like how we wanted to do this, I think we both realized there was so much to cover. It was maybe easier to go chronologically.
Yeah, go along the timeline.
So actually, I started out as a student in mechanics in a French engineering school where it was a lot about math already and a lot about numerical simulation. So I was doing this, and at some point I got the opportunity to go for 2 years to study in Brazil. And I went there,
Okay.
and this is where I met. So I was in the department working on metallurgy. So yeah, just studying different types of metal, and especially one that was hyper-elastic metal and also had some strange properties that the dentists would use to clean root canals. And so, yeah, this was my first experience, professional experience. So I worked there as a researcher trying to model these instruments that would unfortunately sometime break inside the root canal.
I'm going to have to put a trigger warning on this episode.
Yeah. But actually it kind of reconciliated me with the dentist. Like after this, I was much more apt at going to the dentist than before, much less scared. So I was building a mathematical model to describe the motion of those instruments and how the material would behave while inside the root canal.
So this is like you've got specialized tooling made of specialized metals that's spinning at 1,000 revolutions per minute.
Yes.
Drilling into, let's call it calcium and keep it detached from the physical experience.
Yeah.
And how do you do that? What's the programming that goes into that?
So at that stage, the only programming I was doing is like using something like Mathematica to compute to make integral calculations. So it was a lot of integral calculations. I had to just solve this math problem with lots of integrals and lots of variables, and it was super complicated. I could not solve it by hand, so I was using a tool like it was named Maple at the time to do that. So it was my really first experience with programming. It was really using something that does some math.
Okay, tell me a bit more about that, because that's a programming language I've never touched, never used, and I can't quite imagine something dedicated to solving integrals. What's it like?
It's not dedicated to solving integrals. It's more like a generic math software where you can write some equation and it solves it for you. So you write you want to find the roots of a polynomial, you write your polynomial and you ask it to find the roots, it will do it for you. So
Okay.
it's, but you can also give it an integral and it can try to simplify it, to compute the result of the integral, and so on and so forth. So there are many things you can do with this kind of tool.
Does it also do like theorem proving? Is it that kind of area?
I don't think it can do theorem proving, but it was a long time ago, so maybe things changed.
I think there are like two branches of maths. We have numbers or we don't have numbers.
Yeah, exactly. It's like the theoretical part of the math. Yeah, definitely.
Yeah, okay. So from dentistry, I know eventually I want to get to this point where you start delving straight into the GPU.
Yeah.
So what happens from there?
Yeah. So actually, classical mechanics, it's all the same. The way you describe a solid, a metal, a plastic, water, air, the equations are the same. It's just the forces, the way we describe forces, so the way pressure gets distributed and so on and so forth, changes depending on the material.
Okay.
And also, if you can sometimes simplify problems by restricting the kinematics, like the way things move. Sometimes they can't move in every direction, so you can restrict that. But overall, the theory behind it is all the same for water, for metal, for rock, for anything.
This is like when I was at school and the physics teacher said, pretend this is an ideal solid, this kind of thing.
Yeah, so when you say pretend it's an ideal solid, it means like write your forces in a certain way and just make these specific assumptions to just simplify your equations. But the theory behind it is the same
right.
for even for magneto hydrodynamics, like this kind of complicated thing. It's still the same kind of theory behind. So when I was working on solids for the dentists, I had this opportunity to start a PhD in Paris area, working with my previous teacher in the fluid dynamics course, and to work on simulating water flows with a technique that's called smooth particle hydrodynamics.
Okay.
And this technique is like, so it's the same kind of equations. It's just, as I said, the way you describe the behavior of the material changes. And this actually changes a lot in terms of math and what you have to do later to do simulation. And in this, the PhD I was working on, we would describe the motion of the fluid with particles that move. And so for me, there was a strong link because I knew that my PhD supervisor already, I knew he was extremely good. I knew he was like, I really wanted to work with him. So I accepted to start the PhD. It was a French thing where you can do a PhD in a company. So I was working for the main electricity company of France. It's called EDF.
Right.
And yeah, I worked there for 3 years on simulating water flows. And as I started my PhD, we could do a simulation of 100,000 particles in something like half a day or maybe a full day.
Right. Okay.
And it was a Fortran code that they had, and I realized this was not going to work out because just to make small experiments would take me days. So in my team, there were already some people looking at GPUs. So this was in 2012, so pretty early on, because CUDA, I don't remember exactly when it started, but in 2012 it was still pretty early to use it in another context than video games, And
Yeah.
so the people in that team, they started like looking at how we can use it. How they could use those GPUs to accelerate what we were doing. And there was already a team, like one team in the world that was doing this, and they had developed an open source code with GPUs doing this kind of thing. So they took over that code and they modified it to adapt to specifically to the technique they had been developing in the lab. And so I started working on it with them. So it was like we had these geek parties every Tuesday evening where we would go and try to plug the GPU. We like build a desktop, install everything on it. It was like, a lot of fun.
Okay. But so here's where we get into, let's start with my ignorance of how GPUs work, and you can educate me, right? Because I think of GPUs as, okay, they're great for drawing lots of polygons. That's where they came from. And they're really great at doing lots and lots of simple but parallel maths.
Exactly.
Right. Now you're giving me this mental image of imagining fluid dynamics as I'm picturing it as a big bucket of billiard balls, all of which are trying to jostle around.
Yeah, totally.
So
and every ball you have to compute at every time frame during your simulation, you have to compute its interactions with its neighbors.
That's the thing I was about to say, because that's where 100,000 billiard balls moving, that sounds easy on a GPU, but colliding with each other, that sounds like the whole parallelization thing has just completely broken down.
Yeah, you're right. So that's why it's not so easy.
Okay.
So each particle would interact with something in 3D, like with 300 or 500 neighbors. And for each of those neighbors, you have to compute quite complex interactions, let's say. Depending on your algorithm, like depending on the math you chose to use to describe the simulation, it may be more or less parallel. But yes, you have to have some kind of synchronization there. So it's not like it's not ideal in terms of acceleration on the GPU, but we were getting much better performance than on CPUs. So definitely, like it was day and night. So when I started using this, so at the beginning of my PhD, I think after 1 year, I implemented matrix inversion so I had to, in my PhD, the technique I was trying to develop is to solve a matrix inversion to compute the interactions between neighbors.
Right.
So for each particle at each time frame, I would solve a matrix inversion. And so I programmed it because it was not any matrix. I knew the exact shape of the matrix, so I could have a dedicated algorithm for that. And so that's the first thing I ever implemented on the GPU is this matrix inversion using an iterative solver. So it's pretty classical, actually, in terms of software engineering. It's pretty classical, like. And I think it's something in my career that comes back is that in the end I work on very different topics, but it can all be broken down to kind of classical computer science problems. Many people have been working on and so on.
Okay, take me another level down because I'm trying to picture how this will actually work. Because my knowledge of collision detection drops out at 1980s video games.
So in this case, they would not collide the particles. The equations that you solve to describe the motion of the fluid would prevent them from colliding. Except it was not totally working, so you had to have some extra terms there to kind of really prevent them from colliding too much. Because this could make your simulation blow up. Like if the particles got too close together, at some point you would try to divide by 0 or something like that. So it would not work out. But the particles you would not try to detect collisions between particles in this type of method. You would really describe the motion of the particles with some equations, and those equations you would make it so that they don't collide. Like it's the beauty of the math behind it, but also it's very hard to achieve in practice because also of some numerical effects that mix up with the physics when you do your simulation. So that's what makes the thing really complicated. It's like how using floating points, for example, even in double precision, introduce some errors in your simulation and introduce this kind of drift, and how you can mitigate that and so on. So yeah, the whole topic of
this is into the whole chaos theory, butterfly flapping its wings in your fluid thing.
Yeah, exactly.
Yeah.
So there is a famous example of I don't remember. I'm not so good at names, so I don't remember the name of the person. I'm sorry. Okay. But that person was trying to make a fluid simulation with another method. It was, I don't remember the date either, but it was pretty long ago. And he was trying to do this simulation of a fluid inside a pipe, and the pipe would extend. And this configuration, the configuration he was simulating, in his simulation, the fluid would never go the same way. Like he would run it once and it would go downstairs, the main flow. He would run it again and it would go upwards. And he was like, okay, I have a bug in my program, you know? Yeah. And after some time, he realized it was actually a physical effect. Like this specific configuration he was trying to simulate was not stable because of this butterfly effect you're talking about. And the very tiny differences in floating point arithmetics would make the flow go up or down, and it was normal. It's
you iterate that much, and these infinitesimally small changes start to add up. Yeah.
And it has effects on the whole dynamics of your flow. It's not just like tiny effects; it's a major change on the shape of the flow. So yeah, fluid dynamics is complicated because of this, because of the nature of what you're trying to simulate.
So what can you actually simulate? I mean, because I'm thinking of like weather simulations, they become pretty much useless 5 days out.
Yes.
Something like that.
Yes.
What in your situation, what can you genuinely simulate and predict?
Yeah, so fortunately, the viscosity of water is much higher than the one for air. So the characteristic time for this chaotic problem is much longer. And usually we would simulate things that occur within minutes or hours in my lab. So we had some models that we would use to describe in a macroscopic way, so in a high level way, the effects of turbulence. So turbulence is this phenomenon where you have lots of bubbling in your flow, and we would have some models to describe it, because this bubbling, it occurs at large scales and it occurs at very small scales at the same time. And so we could not afford to have such a high precision description, like so many particles, to describe the whole fluid. So we had some models to describe this effect of the turbulence.
How does this, maybe I should step back a second. You said you were doing this for EDF, the French power company. Why is an electricity company doing fluid simulations?
Every energy company is doing fluid simulations.
Why?
Because to produce energy, you have several choices. You can build a nuclear power plant, for example, in France. And this is a big boiler.
Oh, okay,
this is a giant boiler, basically. And it's the same with coal or anything. It's like you have this giant boiler and you have circuits of water cooling down the core of the boiler. And those circuits, everything is flowing inside it. Even you have very complex interactions between the nuclear physics inside the core and the water. It's extremely complicated. I was not working on that, but there is a whole research department at EDF working on that. But you also have interactions with the environment, and this is where I was working. So you have potentially you're close by the sea, and you have storms coming in. You can have, I was doing some tsunami simulation, flood simulation in rivers, because the plants usually they are close to a water source. So whether it be a river or the sea, you have to know what's going on around the plants. And if you choose to use wind energy, it's still an airflow. And so simulating air and water, it's the same equations as well. And yeah, so I think maybe the solar energy is the only one where you don't need it as much. But yeah, otherwise everything you have and also was working a lot with hydraulic engineering. So dam, how do you call this in English? I don't remember, but using dams and turbines to produce energy. Hydroelectricity. Yeah, exactly.
Yeah. What's the famous one in America? The Hoover Dam, right? That's the one I always think of when people mention hydroelectric power. Yeah.
I have lots of French dams in mind, but nobody knows them. So yeah, I was also doing like turbine simulation, producing water, like different types of turbines in different types of rivers or waterfalls. And actually, we were also trying to do waterfall simulations, which is extremely complex.
Yeah.
Yeah, but you have dams where when the flood comes, the water flows above the dam and falls, it's a huge waterfall basically. And we were trying to study the effect of that waterfall on the ground just below the dam. And so to do that, you have to really understand the physics of the waterfall itself. So we had also lots of people doing experiments, not just numerical simulation, but lots of experiments on environmental flows, including waterfalls. Yeah.
Are you visualizing this at the moment? Is it all just matrices being chewed through, or is at some point is there like a video graphic simulation of how you can check your work?
Yeah? Yes, we were also working on this. So we also had some kind of ray tracing software to rebuild the surface of the water and the reflection of the light on it, so that we had a kind of real life visualization of what was happening.
That
was really useful, actually. It was for the waterfall simulations. It was actually to compare with high-speed cameras photography to be sure we are reproducing the shapes of the substructures of the waterfall, which is complex.
Does it work? I mean, I was thinking there's that thing of where you go from the microscopic up to the macroscopic and never quite matches because the worlds are so different. How accurate were your simulations?
Yeah, so actually this is the beauty of these equations that we use to simulate the fluid, is that I'm not sure if I can define exactly the degree of precision for these equations, but it's really amazingly accurate. Like when you look at it, it really looks like reality. But what we were trying to achieve was not only looking at it and making it look real, but also having the right levels of pressures and the right levels, the right velocities, because this is actually what's important for designing any kind of protection or understanding the fatigue of a structure or anything like this. You have to have the physics right, not just making it look real, because this is pretty easy to make it look real, but to have it actually right, the right pressures, the right velocities is much harder. And yes, for this, we're getting really good results as well.
Okay. And so let's get back into the programming of it then. How is this? I'm trying to imagine what your day was like. Did someone come with a bunch of measurements for a dam and you had to write a new program, or were you writing a generic
It was
simulator?
A generic program. Yes, it was a generic simulator. So when we had a new thing to simulate, we would first make a numerical model of it, build maybe we had some scans, for example, and we had to clean up the scans to have a certain distribution of points on the surfaces, and then we had to fill it with particles representing the fluid. So we had these pre-processing stages, and then we would the software we were developing would run this simulation. So we would have some way to set initial conditions and so on, and then we would post-process the results. So we used this tool named ParaView, where you can do some frames, visualize some variables in your simulation, and so on. And basically, that's how we would proceed.
Okay. And what are you writing this in? Is it still Mathematica?
So, no. So the preprocessor tool I think it was, I don't remember actually. It was a long time ago, but I think it was written in Fortran at the start. Maybe we wrote it, I don't remember. But the main software for the simulation, it was written in C++ CUDA.
Oh, okay. Yeah.
So CUDA is this language that you can use to program NVIDIA GPUs. You have some alternatives, and now you have more and more, but at the time it was really the most efficient way to program a GPU. I believe today it's kind of still the case, even though you have Vulkan coming in, but I'm still today working with CUDA programming.
Okay. And is it like, excuse me, is it like, I mean, the only language I know I can imagine code for is like web shader languages, right? Are you converting your mathematical model into something that looks like a GPU shader, or
no? Because CUDA is generic. Yeah, it's a general purpose language. So basically, you write C++ code, and there are some kind of, so you have to just change the way you write it, because you are writing what happens within each thread of the GPU, and you have to organize how those threads cooperate within blocks of threads. So the logic for how you write a program is different, but it's C++ with some additions, let's say, that make it possible to configure how you launch things on the GPU. So how many threads you're going to launch, what is going to be the size of the thread blocks, and so on and so forth. And there are some things you can use on the GPU to make things more efficient. For example, you can use something named shared memory, where threads can have access to a shared memory pool, let's say. So basically, it means you will read from some memory that's faster to access than the global memory of the GPU. So there are lots of low-level optimizations to be made there to really achieve best performance on the GPU, and that CUDA, this language, allows you to make. Okay. So today, it's like, for example, they introduced, I think in 2012, they introduced these tensor cores in the GPUs, and you also have some types of instructions to use those tensor cores to perform matrix multiplication. So, but at the time, we were using things like texture memory that were like very video game specific. Now I don't use this anymore in my job, but at the time we were using this texture memory, things like this to make things more efficient.
So, is it then that you're I'm trying to get a feel for this? Is it that you're writing code for the GPU which could be like classical linear code?
Yeah,
it still run.
It really looks like C++ code.
Okay, but then you're trying to be aware of all the hardware level tricks where you can optimize and parallelize.
Yes. And also the logic of how you write things is slightly different. Like you don't write a for loop. Instead of writing a for loop to do something, you will write something named a kernel. And in the kernel, so this function that's named the kernel, you describe what happens per thread, what each thread does. And then you configure that kernel to use a certain number of threads, a certain number of block threads, and a certain amount of shared memory. And then you can have some more complex things where you can also streamline work on the GPU. So you also have this type of choice. But basically, GPU programming comes down to this. And inside the kernel, there you can do the low-level optimizations of really how you want things to happen on the GPU.
Okay.
Yeah.
Does this mean that a large part of your programming is understanding the specific GPU card you're using, or is it more general than that?
Yeah, so definitely that's a big part of my work. And also understanding how the NVIDIA compiler behaves when I write some things. Usually I don't understand, so I have to just try it out and see what happens. And,
that sounds very familiar programming, yeah.
But yeah, and then every generation of GPU comes with some changes, so we also have to adapt to this. And there's also this dimension where you can use multiple GPUs to perform computations. And already during my PhD, I was doing multi-GPU computations. So then you have to coordinate what each GPU does, when, and how it collaborates with the others. So you have synchronization at the kernel level on the GPU, you have synchronization between kernels, you have synchronization between GPUs. So yeah, it's a lot of parallel programming.
Right.
Asynchronous parallel programming, yeah.
Does it end up looking something like pipeline-based programming, where you have...
It can. So part of it is something like that, yes. But you also have like the lower level stuff where you can also, but it's the same on a CPU. You can also write some lower level things like using specific instructions to accelerate specific parts of your code. But you don't have access to, like on the GPU, you can really decide what area of the cache you're using, for example. And you have to really be sure you don't use too many registers. So it's like, it's a lot of small optimizations to make before you reach the best performance for a specific function.
Yeah. Diving into all those things we tried to abstract away from in the 60s and 70s.
Yeah, exactly. I'm an old timer, actually.
We're kind of going backwards through time if you're now worrying about registers.
Yeah. No, but because on GPUs, it's really something you want to monitor. Because it's you define what happens on a thread on your GPU, and you define how many threads you want to launch, and then the compiler schedules everything for you. So you're not writing the scheduling of how each thread will be executed. This is the compiler that makes it for you. And depending on how you wrote your functions, your kernels, then you achieve different occupancies on your GPU, meaning you can be using 100% of the cores all the time, or you can be using 10% of the cores all the time. And you can already have an intuition that if you're only using 10% of your cores, your performance is affected. So the occupancy on your GPU, so how many cores are actually being used at this, during time, is determined by how many registers you use, how much shared memory you use, how many threads you're launching, and so on and so forth. So that's really something we try to monitor closely. And a big part of my work is to try and find an optimal value for that occupancy. Because 100% occupancy is not always good either. It usually means you're just running too many small tasks in parallel, and probably there's a better way to do it.
Oh, I see. Yeah. So how much of your job is writing new code, and how much of it is like digging in and optimizing existing code?
Oh, good question. I think in my job, I dig into the code and optimize mostly. I think writing new code, I did it. I don't know. It's hard to tell. It depends on the moments, actually, because sometimes you writing something for the first time is pretty straightforward. Let's say you don't try to optimize everything the first time you write something. You want just to be correct first, and then it takes a really long time to make it optimal. Yeah.
Okay.
And to debug, actually, because debugging is a big part of my job. Yeah, I spend a lot of time debugging.
Yeah, I can totally believe it. Maybe we should go into how you do debugging on this. Actually, let's do that. Let's go into how do you debug these pipelines? What kind of problems come up? What tools have you got?
Yeah, so we have a debugger, CUDA debugger, so you can know what happens exactly in your kernel on which thread and at what time and so on. But it's complicated to debug because many things happen asynchronously. So if it's a synchronization bug, it's super hard to detect where it comes from. So how I debug is also mostly printing stuff. Sorry, but I do this a lot. Like I print stuff in my program and I try to understand like why this variable is changing now, where it comes from, the change, and so on. Many times we have also like memory bugs where we're trying to access memory in a place in an array that's not correct. Maybe it's allocated, but it's not the right place. So this is extremely hard to detect because it's not going to be the debugger won't detect it because memory is valid. It's just not the right value you're fetching. And so this is actually very problematic. I think maybe the worst bugs are those ones, the synchronization bugs and those accesses to places in arrays that are not the correct ones. This is and so in the CFD world, so in my fluid dynamics work, it was already very hard to debug because there are so many particles doing things all together. So to know exactly, and when you have a small bug that's only affecting one or two particles, you don't really see an effect on your whole simulation.
Yeah.
At least not until a very long time. So
Yeah.
it's very long to debug.
It's hard to
And
see in the rest of the
actually,
noise.
yeah. And now after I worked in this fluid dynamics project, I worked also at EDF for some time. After that, I switched because I was working in a research department, and I really wanted to be working more with software developers.
Okay.
I wanted to be in a team of software developers, and so that's when I joined this the power grid operator in France that's named RTE, and working on software, a Java software, no more GPU there, that was doing power grid simulation.
Okay.
So power grid simulation is the same physics. It's just for most things, it's a lot simplified. We don't simulate all the physical effects, and to me, it looked more like building a huge Lego software because you have all these equipments in the whole country, in the whole of Europe. I mean, we were focusing on simulations for France and for Europe. So you have all these equipments that have different characteristics, different physical behaviors, and you had to represent them in your software and make sure everything was conformant with the actual equipment on the ground and so on. So it was like assembling lots of Lego pieces to me.
So what kind of things what level of detail are you simulating there? Are you simulating the kind of, I don't know, ampage that a particular cable stretching across Marseille can take?
Yeah. No, so it's the high tension lines that we were simulating.
Okay.
So it's like the highways of electricity. For all of this, yes, we monitor the amperage, voltage, everything that would be relevant to making decisions, making real-time decisions for operators of the electrical system, and also making market decisions for like provisions of how the grid would be operated within 3 years, 1 year, 1 week, 1 day, 1 hour, so also making these kind of provisions. Yeah. And so for me, it was a lot less math. There was no more GPUs. It was a lot less about optimizing things at a low level. And I think I was missing it probably. But I got this opportunity to work for a company that was based in Paris that's named Zama, and that was building this cryptography technique.
Yeah, you're heading back to the GPU, but this time for crypto.
Yes.
Not for crypto. I almost said crypto. That's a very different thing.
Yeah, so for cryptography algorithms.
Let's be clear on that.
Yeah. Yes. And so I completely moved away from physics. Now I'm not working with physics anymore, but I'm still doing the same kind of things. I'm still programming GPUs to accelerate complex algorithms. And I think that's really something I really like to do in my job. And so I'm pretty happy to be doing it still. I'm happy with the change.
Okay.
So maybe I can just give an idea of what this cryptography technique is and what it means to make it faster.
It's got a cracking name, hasn't it? Fully homomorphic encryption.
Yes.
Right.
Yes, right.
Explain that.
Yeah, so basically, everything we do when we interact with the internet or anything like this is encrypted in transfer. So when you want to perform some computation on data today, you encrypt it, you send it encrypted to a server, and the server will decrypt it and run computations on it.
Yeah.
What this technology, so fully homomorphic encryption, I will name it FHE, what it allows is to encrypt your data, send it encrypted, and the server will perform the computation on the encrypted data without decrypting it. We'll send you back the encrypted results, and only you can decrypt it.
Now, on the surface of it, that sounds impossible.
Yes. What makes this possible is by writing a cryptographic scheme that has some mathematical properties that makes this possible. It's below the hood. It's really some mathematical properties of your cryptographic scheme that makes it possible. And so depending on your schemes, you have different properties. So many cryptographic schemes, you can add ciphertexts, and the result of this addition is the encryption of the addition.
So I'm going to have to go slowly on this to make sure I'm following. So I've got one document I encrypt, I've got another document I encrypt, and I can concatenate them and still get the meaningful concatenation of the two encrypted documents back out.
Exactly.
Okay, I don't know how that's done, but I can imagine a mathematician figuring that out.
Because what you do when you encrypt something is you make your data look random. Basically, it's the core of cryptography. Everything has to look random, and nobody can make the difference between your data and an actual random number generated by a computer. And so the way you make it look random, you can imagine lots of ways to make it look random, but the algorithm you choose to do it, depending on it, you have some properties on the scheme itself. On the ciphertexts, you can perform additions. Sometimes you can perform also multiplications. Sometimes you can perform only a limited number of additions or multiplications. And today, with the technology we're developing at Zama, we can perform any number of operations and any operation. So that's really powerful. It's something like people have been thinking about since the 70s, and it only became possible in 2009 with a paper by Craig Gentry, who thought of a technique to. Okay, I have to explain some lower level things to explain this, but basically in the technique we use, we hide the message with something that looks random, and we also add some noise to it.
Okay.
And the problem when you add two ciphertexts is that this noise grows. When you multiply a ciphertext with a clear value, your noise grows. And if your noise grows too much, you corrupt your message. And so in 2009, Craig Gentry came up with a technique that allows you to reset the noise in your ciphertext to a nominal value. And that was a game changer because now you can perform as many operations as required for your circuit.
I still can't see beyond the veil to how you perform these. Because you're saying this is all happening without the person doing the addition, let's say, decrypting the message.
Yes.
So I've got two big numbers that have been encrypted. I am now going to be able to multiply the encrypted versions together without knowing what the numbers are.
Yes. And the mathematical property of the scheme you use to encrypt, with the addition, it's more simple to visualize it. But in the technique we're using, we are it's complicated to explain in just a few words, but we are basically hiding the message with something that looks random.
Okay.
And this thing, when you add two of them together, they add up. So when you decrypt, you get the result of the addition.
Are you saying that I'm adding the two numbers and adding the two sets of noise, and when someone goes to decrypt it, they can remove the added, the summed noise and get the summed value back?
Yes, basically that's it.
Okay, and this guy, Craig Gentry, if you do lots of these operations, the noise gets larger and larger and larger until it obscures it, and this guy, Craig Gentry, figured out how to reset the noise without decrypting?
Yes, exactly.
Okay. Okay.
This is complicated, yeah. But basically that's it. And the thing is, when he had the idea, it was impractical because it was way too slow to do that. So when Zama, my company, started, it was still very impractical to use this kind of schemes. But today, it's I think since Zama started, I think it got 100 times faster. So now we are really getting into a stage where we can use this technology in practice, and that's very exciting.
Give me some idea of the times we're talking. What define slow and 100 times faster than that?
Yeah, so depending on your scheme, computing on encrypted data can be 1,000 times slower than computing on the clear data.
Okay. So you've lost 3 orders
So
of magnitude on your addition operation.
yeah,
That's painful.
at least. I think maybe it can be more, or it can be less, depending on your requirements in terms of security and precision of the computations. But yeah, it's about that, and we are still, we still need a lot of acceleration for this technology. But it's really like, it's something so new that first we are targeting use cases where speed is not so much of an issue.
Okay.
When we can afford to have some latency in the computations. So that's why the first clients for Zama are in the blockchain field.
Not surprising.
Yeah. And so because there we can afford to have some latency, and so it's much easier to have businesses being built around this technology than, for example, in AI, where it's already very computationally intensive. So it's very hard to make it practical to use the technology and have a real business value there. So we are also working on it. I think we're still missing some acceleration there to make it actually practical.
But okay, so speed aside for the moment, what's the use case of being able to do operations on a large language model that's encrypted without decrypting it? Why is that good?
Well, it means, okay, usually when you perform this type of computation, you send your data to a server, and you're not the person who controls the server. So you have to trust that server, and also you have to trust that server is protected against attacks, So having everything encrypted end to end, it means you are intrinsically protected against this. It's like
So
you could have, for example, personalized adverts without Google ever seeing your data, for example.
okay.
It's
Or I'm thinking I'm running a legal firm and I'd like to be able to search all my case histories. So I want someone to build a large language model around my case histories, but I don't
yes,
want to send my client's legal documents to you.
exactly. This is
Okay.
or in the healthcare industry, finance
Yeah.
industry, everything that holds sensitive data basically is impacted.
And I can see a reason why you want someone else to build the large language model for you.
Yes, you don't
Without
want to
bringing that in
have
house.
thousands of GPUs in your
Yeah.
in your office. It's not viable.
Okay. Yeah, I can start to see that. I see the use of it. So this is why they've hired Agnès Leroy, because there's a use case for it, but I can see why that would be slow.
Yeah.
Tell me how your job has gone optimizing that.
Oh, so basically, when I started out, we were focusing on optimizing one specific operation, that's this bootstrapping, that reduces the noise in the ciphertexts, implementing this on the GPU and making it as fast as we could on the GPU. And at first, it was not clear what our target was in terms of optimization, because we didn't know if we wanted to be focusing on the throughput. So being able to achieve thousands of these bootstraps in parallel as fast as possible, or if we wanted the latency of one of those operations to be the smallest possible. So it was something that came like with the growth of the company and the fact we had first clients, it became clearer what our targets were. And my job became simpler because I could really focus on these objectives. So this function is extremely hard to accelerate on a GPU. It's a little bit like the fluid dynamics thing. It's not really fit for a GPU. So at first we didn't get any speed up. It was terrible. But that's expected. Like also like the CPU code we were comparing with was getting a lot more optimized as time went by. So we were comparing with something that was always getting better, which was good actually.
Meanwhile, you're losing time. You're losing time in the race because you're converting it over to run on the GPU for starters.
Yeah.
Right.
But
okay.
But that's also expected. Like this is something I had already experienced in the fluid dynamics, my fluid dynamics work, and so when we started actually focusing on implementing specific integer operations on the GPU, then we started to have like much better speed up. Because then we were really able to fine tune the implementations for these specific amounts of bootstraps we would be running in parallel and so on. So that really changed a lot. And now we are able to have 3 times better performance on the GPU than on the highly optimized CPU implementation on very large CPUs, running on very large CPUs. So we're really comparing on hardware that are like top of the game. And also NVIDIA has been releasing the Hopper GPU. They released it like a year and a half ago, maybe, or more than a year ago, or 2 years ago. I don't remember. But this GPU is like really much bigger than the previous ones. So that also helped a lot in terms of performance on the GPU. And we also see this trend continuing in the future. Like NVIDIA is going to release bigger and bigger and more powerful GPUs. So that's also something that will help a lot for us. But yeah, it's these new GPUs. They also come with new features. So we also try to adapt our software to use these new features as best as we can. So it's very interesting. We are like really up to date with the newest things that come up on the GPU world. So that's very interesting.
Give me an example of that. What counts as an exciting new GPU feature?
So at first we thought we could use the tensor cores. So maybe just one thing is that, I said in fluid dynamics, everything I was doing was coming down to invert computing matrix inversions. Here in the cryptography world, everything comes down to computing polynomial multiplications.
Okay.
Lots of polynomial multiplications. So very classical algorithm again. Yeah. And to do this, we use the fast Fourier transform algorithm.
Okay.
So we are trying to accelerate the execution of thousands of fast Fourier transforms in sequential and in parallel on the GPU. So it's basically what we're doing, also using multiple GPUs and so on. So now I forgot why I was saying this.
We were talking about exciting new
exciting
hardware
new features.
So
so at some point we thought maybe we could use the new tensor cores on the Hopper GPUs to perform those fast Fourier transforms. We needed a tensor core that could deal with the data types we are using, which is a double precision floating points. And this was released in the Hopper GPU. But actually, in practice, it proved that it's not so easy because you have to load memory on those cores and to retrieve memory from the cores, and you have to really load them fully if you want it to be very efficient. So for now, we are not digging into that much further. But what we started using was the distributed shared memory feature of the Hopper. So, I told you we can use shared memory within a thread block to have threads access memory faster than if it were on the global memory. And with this feature, you can have different blocks accessing the same type of memory without needing like so much synchronization. So that's really interesting also for us. You can have more cooperation at a higher level on the GPU than before.
That sounds like you're going to run into even more race conditions and memory errors.
I think race conditions is something we're really used to. Bugs, they come up with every line of code. Like it's I don't know. It's like every 10 lines of code you make one bug. I think it was something like this I read sometime online. Like it's crazy the amount of errors and mistakes we make. Fortunately, we have lots of testing tools to make sure we're not breaking anything. And actually, a big part of my work was to build a very strong CI infrastructure. So continuous integration and very strong tests. And the whole team has spent a lot of energy on this to make sure that we are testing everything. Because what we do has noise into it. So this noise makes it hard to actually track what's going on. And everything is hidden and looks random. So when you debug, you can imagine how painful this can be. Because everything looks like a very large, like close to the maximum of the U64 representation number. So it's not so easy. And there are lots of those numbers. So that's funny.
And there's a definite parallel there to the fluid dynamics simulations.
Yeah, Totally.
Very small problems add up.
Yeah, exactly. Very small effects can corrupt your message in the end if you don't detect them. So yeah.
But we are saying that this is, because it sounds like this encryption technique could be something that's lossy.
Yeah, so no, depending on how you do it, it's not. So that's the thing. It's like today, with the technique we're using, we can ensure that the result is correct with a certain probability of failure. But we set probability of failure that is so low that this does not happen in practice. That's how we do it. And to achieve it, we have to make sure the cryptographic parameters are chosen correctly, in the sense that, I said we hide the message with something that looks random. And to build this random thing, we have to use lots of integers, and we can choose how many we use. We can choose the size of the ciphertext, basically, and the variance of the noise we use in the ciphertext, all those things. The real trick in this technique is how to choose them so that you achieve a certain probability of failure, you achieve a certain level of security, and you don't compromise too much on performance. That's really like the core of what we've been doing at Zama. I think a big part of it is this: how to choose those things in a way that makes it possible to use the technique and practical. And that's and
so
secure.
You got the juggling technique of those parameters, the juggling technique of GPU parameters, and the juggling technique of low-level parallel programming.
Yeah.
Okay, you've got plenty of problems. That's good.
Yeah, that's very exciting. But
okay.
The vision for the company right now is that on the short and middle term, CPU and then GPU acceleration will make the technique more performant. But on the longer term, the goal would be to have a dedicated hardware for this technology. And because in cryptography, this is something that happened already. Like today, everybody is using encryption. So this HTTPS protocol is also possible because you have some dedicated hardware in every laptop that does it. So this AES algorithm is actually implemented in the hardware. And so that's why the vision for this technology to really take on is also to have dedicated hardware to accelerate it. Maybe one thing that could be possible is to have some cores in the GPUs, for example, even without speaking of a dedicated ASIC, so a dedicated chip. We could imagine some GPUs that have some specific polynomial multiplication cores. Like you have for AI today, you have a matrix multiplication cores dedicated for it. So you could imagine to have a GPU that has these cores. If we had this, everything would be much faster on GPU.
So is there this thing of you figuring out how to make it run fast on GPUs to figure out what you might go and ask NVIDIA to implement?
Yeah, totally.
Yeah.
NVIDIA or AMD or it's
whoever.
Yeah. Whoever, but definitely it's something that's very important to know exactly, because it's not any polynomials we are multiplying. They have a specific size, so it's when you try to implement a very generic polynomial multiplication thing, it's complicated because you can have any size of polynomials. But when you know your polynomial is a certain size, you can really fine-tune everything to fit that size, and that's really very different. Yeah. So the tensor cores today, they were made to be able to handle any size of matrices. But I really think if NVIDIA had implemented something to only multiply, so right now I think they can multiply 4x4 matrices, depending on your data types, it may change, but something like this, and then they combine them to multiply very large matrices. So really, it's like also trying to experiment with different fast Fourier transform algorithms is super important in our job, and we are also trying to see, like, when we switch algorithms, what happens in terms of performance, how it behaves on the GPU. How we try to imagine, like, how in the GPU this could be integrated, embedded in the hardware as well.
Right. Yeah. Because I've seen this thing where sometimes people choose a seemingly slightly worse algorithm because it maps to the hardware much better.
Yeah.
Okay. I think I have to ask you one final question, which maybe maybe slightly flammable. But I've got to ask, right? So it seems to me that a large part of your programming job is dealing with things like memory errors, register allocation, memory safety, parallel programming, all that stuff.
Yeah.
Meanwhile, I look at the history of the CPU-based world, and the move is away from very low-level languages to, I mean, it's easy to pick on, say, the drive to go from C to Rust to get the compiler to take care of these safety issues for you.
Yeah, that's where things have to go.
Yeah. Do you think is that something you would like to see happen in your world? You're using,
yes.
Yeah. So you would happily get away from C++.
So actually, half of my work is also in Rust because we integrate our CUDA library in the Rust project that we have that's for the CPU execution. Okay. And so I worked a lot with Rust since I joined Zama, and I can 100% say I would love to have a Rust equivalent of CUDA because this is like changing your life. Totally. This is my dream. And I know there is a project trying to do this. So I hope that soon this will not be a dream anymore and I will be able to switch and to have some compiler safety, ensure the rules.
Save some of your debugging time.
Oh yes, totally.
Okay.
Because Rust is so powerful. Like for me, it's something every developer should look at. If you have the choice between writing a program in C++ or writing it in Rust, for your own sanity of mind, please choose Rust.
Okay.
And there are some drawbacks, and especially it's a bit hard to learn Rust, I guess, or at least that's what I seem to see with people. Like they tend to have a kind of a hard time getting started with it. But you really have to talk to the compiler. The compiler talks to you. You have to read what it says, understand it, and once you've done this, things get much clearer, and the pain of using Rust goes away, and you only see the advantages. It's like, yeah, for me, it's 100% in favor of Rust.
Okay.
If I could, from the start, I would have written the project in Rust, but to configure the kernels and to write the kernels, we have to write them in C++. So for now, we are still there.
Okay. It sounds like the future episode of this podcast needs to be with the people developing a Rust-based CUDA.
Yes, that would be amazing. That would be really amazing.
Groovy. In the meantime, I shall leave you to go and optimize what you can in C++.
Yeah, thank you.
And yes, thanks very much for joining me. That was fascinating.
Thank you very much. Thank you very much, Chris. It was a pleasure.
Cheers. Thank you, Agnès. I have to wonder, after all that, are more people going to be disturbed by the image of stress testing dentist tools for root canals, or by the critique of C++ versus Rust? Tough to say. Hopefully neither, but, if you've been troubled by any of the issues raised in this week's podcast, our contact details are in the show notes below. But you should probably just have a cup of tea. That's probably for the best. I'm going to go and have a cup of tea. Before I do, I shall just say, if you've enjoyed this episode, please leave a like. If you want to support this podcast and future episodes, go find us on Patreon. And make sure you're subscribed for next week's episode. Until then, I've been your host, Chris Jenkins. This has been Developer Voices with Agnès Leroy. Thanks for listening.